Okay, so we're going to go over nth roots and rational exponents. So first of all, nth roots. When we say nth roots, so it's really just like extending the idea of square roots. So an nth root, first of all, a square root we know is like x squared is 25, so then the square root of 25 is x, right? So it's just the opposite of squaring something. So we can extend that idea to any kind of radical. So for instance, 5 cubed is 125. Then we draw, it looks like a square root sign, but it has a 3 on the, sitting on the corner right there. So the cube root of 125 is equal to 5. So we're just reversing the operation of cubing. Similarly, the fifth root of negative 32 is negative 2. Because if I do negative 2 to the fifth power, that gives me negative 32. Alright, so a radical sign. So this number right here is called the index. That tells you what type of radical you're taking. If there's no number written there, then you know that's a square root. So then the actual sign is called a radical. And then the number inside this is called the radicand. Okay, so in simplifying radical expressions, just like when you simplify square roots, you want to pull out all of the factors that are perfect squares, and then you want to make the index as small as possible. And you want to make sure that no radicals appear in the denominator. The no radicals in the denominator is kind of a weird rule, but we'll get to that later. So here, in this first example, we have 27x to the 8th power, the square root of 27x to the 8th power. So in simplifying these, just like when we simplify radicals with only numbers, we can split this into simplifying square root of 27 and simplifying square root of x to the 8th. So since we're simplifying a square root, we want to find factors that are perfect squares. So 27 splits into square root of 9 and square root of 3. And then square root of 9 is 3. So, similar to when we were simplifying those exponential expressions, when we simplify radical expressions, it's kind of helpful to sort of deal with one variable at a time. So now in simplifying x to the 8th, so I want to find if there's something that I can multiply by itself to make x to the 8th. And in fact, because it's x to the 8th, that would be the same as having the square root of x to the 4th times the square root of x to the 4th. So that's essentially x to the 4th squared. So what happens is the x to the 4th can come out of the radical since there's 2 of them, right? And then we're just going to rewrite this. Usually when you simplify a radical, you write the radical last. So it's going to be 3x to the 4th times the square root of 3 as our final answer. Or 3x to the 4th root 3. Okay. Number 2 now, we're dealing with a 4th root. So rather than look for factors that are perfect squares, we want to look for factors that are perfect fourths. So things that are perfectly raised to the 4th power. So the 4th root of 32, and you start seeing these things the more math you do, but I know 32 is actually 16 times 2, and 16 is equal to 2 to the 4th power. So 2 times 2 is 4, times 2 again is 8, times 2 again is 16. So I can pull out a 2 from there, and then I'm left with a 4th root of 2 inside the radical. So that was just the numerical part. 4th root of a to the 24th power. So in this case, we know that in properties of exponents, a power raised to another power, so we have this power. So if we have a to the power of x and then to the power of y, that's the same as a to the power of x, y. So really, we want to find whether there is something that 4 times something gives me 24, because that's what's going to undo my fourth root. And in fact, 24 is the same as, so this is the same as a to the 6th to the 4th power. So that's the same as having the fourth root of a to the 6th raised to the 4th power. And again, a to the 6th to the 4th would make a to the 24th. And then since these are now inverse operations, the fourth root effectively is the inverse of 4th power, so those things can cancel each other out and then leave us with just a to the 6th power. So keep in mind, the radical sign is attached to the entire fourth root thing, right? So it's not like the 4 cancels and the radical stays. The whole thing is gone, right? Okay. So now we have the b to the 13th term. So it's the fourth root of b to the power of 13. Now 13 isn't divisible by 4, but just like kind of how we split up square root or fourth root of 32 into something that was a perfect fourth and something that wasn't, we can do the same thing with b to the 13th. So this is the same as the fourth root of b to the 12th times b. And b to the 12th is a perfect fourth power. So 12 divided by 4 would make 3, so that's b cubed, and then the fourth root of b is left inside the radical. So again, the fourth root of b and the 12th root, so those things undid each other, but this b, the other one, has to stay inside because we couldn't take the fourth root of him evenly. So now if we just write this in a nice order, so these numbers are going to be inside of the radical, and all the other numbers are going to be outside. So 2a to the 6th b cubed times the fourth root of 2b is our final answer. So on this next one, we have x to the 6th times y to the 7th. Or square root of x to the 6th divided by y to the 7th. So one property of radicals is that I can split this up. So I can do the square root of the numerator divided by the square root of the denominator. The square root of x to the 6th is pretty straightforward because, remember, it really is as simple as I can do 6 divided by 2, and then I'm left with x cubed. So x cubed squared would give me x to the 6th. So if I square root x to the 6th, I get x cubed. Square root of y to the 7th is a little trickier. So we want to split that into square root of y times y to the 6th. Because y to the 6th is a perfect square, y to the 7th is not. So when I do that, the square root of y to the 6th is y cubed, and then I'm left with square root of y in the denominator. So now we go back to that rule about having radicals in the denominator. It's usually better to not have radicals in the denominator because sometimes you'll get really nice things that simplify. So we want to not have this in the denominator. One idea I hear a lot is that we should square the numerator and the denominator. So that would absolutely get rid of the radical. The problem is that it changes completely the value of the expression. So we can't square the numerator and the denominator. So if we're dealing with this expression here, all we're allowed to do is things that don't change the value. One thing that doesn't change the value is if I multiply by 1. So if I multiply this by 1, I'll get the same expression. But I don't want to use regular 1. I want to use a version of 1 that's going to cancel out my square root of y. And what will do that is if I multiply the denominator and the numerator by square root of y. Because the square root of y times the square root of y will make y, because that's the square root of y squared. So if I do this, I get x cubed square root y in the numerator, and the denominator I would have y cubed times square root of y squared, because I had square root y times square root y, and the square root and the squared are inverses of each other. So in the denominator, I'll just end up with y to the 4th. So x cubed square root y divided by y to the 4th. Alright, and last example on the front is cube root of 2 over 5x. So once again, I'm allowed to split this up. So cube root of 2 divided by the cube root of 5x. So just like in the last example, I can't have the radical in the denominator. And because this is a cube root, it's not a square root. So in order to cancel out a cube root, I need my denominator to be, I need the thing under the radical in the denominator needs to be something raised to the 3rd power. So right now, if I were to just do this, so cube root of 5x over cube root of 5x, that isn't enough to simplify the cube root, because I would only have 5x times 5x, which is a perfect square, but it's not a perfect cube. So the way to deal with that is to do this twice. So now in the denominator, I have this 3 times, or this to the, I have 5x raised to the 3rd power inside the radical in the denominator. So in the numerator, I get cube root of 2 times 5x times 5x, and in the denominator I get cube root of 5x times 5x times 5x. Or another way to write that would be, so instead of writing out 3 5x's, I could write 5x parentheses to the 3rd power. Now we can see this cube root and this 3rd power are inverses of each other, so those will cancel out, and we're left with, in the numerator we get 2 times 5 is 50, and x times x is x squared. That's still under a cube root sign, and my denominator is just going to be 5x. Okay, so on to the next part. So talking about rational exponents, sort of breezed through this in class. Really what we want to get at here is that if I have some sort of fraction exponent, so x raised to the power of a fraction, this is the same as having the nth root of x raised to the power of m. And the order that you take a root and a radical, or a root and an exponent, doesn't matter. So you can also write this as the nth root of x with the m on the inside. These are the same thing. The reasoning for that is best explained if we just look at x to the 1/2. So x to the 1/2, if I square this number and I use my properties of exponents, that's 2 times a half, the power raised to another power. So that gives me x. Well, another number that gives me that when I square it is the square root of x. That also gives me x. So if this thing squared equals x and this other thing squared equals x, then these two things must be the same, right? It's a classic case of like a equals b and b equals c, then a equals c, right? So one thing equals another thing, and then the other things equal each other, so this first thing has to equal this thing. And then if we extend that to higher exponents, so the denominator of this fraction becomes the index on the radicals. So for any x to the 1/n, that's the same as the nth root of x. And then when you have a numerator on the fraction, well, if we have something like this, x to the 1/n raised to the power of m, then that's the same as having this, right? Now, if this is all like kind of over your head and you would rather just remember this part, the one rule, that's fine. I personally forget rules a lot, so when I make sense of rules, like going through this little investigation here, when I make sense of the rule, then the rule makes more sense to me, and I'm able to remember it better. Instead of like trying to remember, does the denominator go to the exponent or the radical, I get mixed up a lot. So I like to try to sort of prove my rules so that I'm able to remember them more easily. In application, this is really pretty simple to use. So convert rational exponents to radicals. So I have a 2 as my numerator and a 3 as my denominator. So the 2 is the exponent and the 3 is the index. And that's it, right? So this went there and this went here. And that's all there is to it. The second example, so notice this is a negative exponent, and that's from our properties of exponents. We know negative exponents make reciprocals, so this is going to be 1 divided by, and again, the 5 becomes the exponent, and the 4 is the index. That's it. This one we have to be a little bit careful because this exponent, the 30, is only applied to the a. It's not applied to the 2. So we're only going to have, so 2 as an exponent would be 2 to the 1/5 power, because 2 has an invisible exponent of 1, and then we're still taking the 5th root of it. And then the a is a to the 30/5. And now you can kind of see, so when we were working on the front with simplifying a to the 30, like the 5th root of a to the 30th, we just divided the 30 with the 5. And now you can actually see that that's exactly what we're doing. So this is the same as 2 to the 1/5 times a to the 6th power. Okay, so this is the same as example 2 on the front, but now we're going to do this with rational exponents. The 32, we'll simplify that one the same way. So if you forgot how we did that, it's on the front. But that's going to be 2 times the 4th root of 2. The rest of it, so we have a to the 24/4, and then b to the 13 over 4. So 24 divided by 4 is 6, so now it's, this part becomes a to the 6th power. And then, since 13 divided by 4 isn't a whole number, what we actually want to do is divide it, but then, so it's like we divide it and we take the remainder. So when I divide 13 by 4, I get 3, but with 1 left over. So I'm going to have b cubed, but then I'm still going to have b to the 1/4. And we can see if we were to work backwards here and add the exponents, so b to the 3rd times b to the 1/4 would be 3 plus 1/4, which would give me 13/4. 2 4th root of 2 can hang out and go for the ride. And now I'm just going to convert my b to the 1/4 back into radical form. So I have 2 times the 4th root of 2b. No, I forgot the a to the 6th part. That's not the right thing. So it's 2a to the 6th b cubed times the 4th root of 2b. So the same answer we got on the front, just kind of a different way. In this one, number 10, so notice we have a square root on the top and a 4th root in the denominator. This one becomes much easier to simplify. Rather than multiplying by 4th roots on the numerator and denominator, this one becomes much easier to simplify if we use our fraction exponents. So first of all, I see square root of 3. I'm not going to be able to do anything to square root of 3, so I'm just going to leave that one as is. All the other ones, so remember, this is it's a square root, so that's an index of 2, which means all of these terms can be rewritten as, so the numerator I have x, my exponent is 3, and my radical is a square root. So x to the 3 halves, and then y to the 5 halves. Denominator, I can do the same thing. So it's a 4th root of x to the, of x cubed y to the 5th. So the 3 becomes my exponent, and the 4 becomes my denominator. And the same thing with y. So y to the power of 5/4. This looks bad at first, but one of the nice things about being able to rewrite this in exponent forms is now I can apply properties of exponents. So to simplify this, I can just subtract 3 halves and 3/4, and that will give me my new exponent on x. So 3 halves minus 3/4 is 3/4, right? So I'll do this off to the side. X to the 3 halves minus 3/4, right? And I'm pretty sure that that comes out to 3/4. Yeah. So my new exponent on x will be x to the 3/4. And similarly, to get my new y, I do y to the power of 5 halves minus 5/4. And that actually also comes out to y to the 5/4. So the fact that these came out to the number in the denominator was just coincidence. My square root of 3 is still hanging out front. And notice I don't have anything left in the denominator because when I subtracted these exponents here, I got still positive exponents. So everything in the denominator is now simplified away. And then my y to the 5/4, I can make this actually turn into, so this is going to simplify my radical because 5 is greater than 4, I'm going to change this to y times y to the 1/4. So now, if I convert everything back into radical form, I have a y out front, and then a square root of 3, and then a 4th root of x cubed times y. And that is my final simplified answer. So this one's nice because it really does come out looking a lot simpler than the original problem. Okay.